Welcome to today's Energy Auditing in Relation to Building Enclosures webinar, sponsored by the American Institute of Architects. At this time, it's my pleasure to introduce today's speakers. Chris Halpin is the president of Celtic Energy Incorporated. He's a lead accredited professional, a certified energy manager, and a certified energy procurement professional. Paul Poppenshaw is the director of engineering at Celtic Energy Incorporated. Paul is also a lead accredited professional. At this time, it's my pleasure to turn the program over to Chris. Chris, welcome.
Thank you, David. Good afternoon, everybody. I'm Chris Halpin, president of Celtic Energy.
And hello, this is Paul Poppenshaw, director of engineering for Celtic Energy.
So we want to thank everyone for being here today and for AIA for giving us the opportunity to do this webinar for you. And since we have a lot to cover today, we're going to get right into it. And as David had said, please type in any questions you have as we go along. Some of the learning objectives today are building energy benchmarking, building energy audit process, the identification of enclosure ECMs or energy conservation measures, and building enclosure impacts on energy budgets, and then your questions. So a little bit about us. Celtic Energy has been around for almost 11 years. In May, it'll be 11 years, providing energy efficiency and sustainability consulting services for large commercial, industrial, government, and institutional consumers and customers. We do everything from energy savings performance contracting, that's ESPC, consulting, where we act as a third party to large government agencies, energy auditing, energy modeling, commissioning and retrocommissioning, as well as carbon reduction consulting and strategic energy planning. And I'm not going to read off the list of our clients, but you can see we do work for a lot of large, both government as well as corporate clients, some of the largest property owners in the world. We have offices here in our headquarters in just outside of Hartford, Connecticut, Boston, Massachusetts, Charlotte, North Carolina, and Las Vegas, Nevada. Topics we hope to cover today are energy and the environment, building energy use and benchmarking, the building enclosure loads and effects, as well as enclosure issues and concerns, the audit process itself for building, typical energy efficiency or energy conservation measures we had mentioned earlier, and audit and inspection techniques, and then finally a conservation project economics and considerations. A few sort of housekeeping notes. Some of the information that we're going to cover may not apply to all climate zones, building types, or clients. We're going to give you some general examples. Some we have very specific, like in, say, Houston and Chicago. Others are more generic. And some of the sketches and diagrams are more schematic in nature, may not show all components of an enclosure elements being discussed, but for presentation purposes, we were trying to make it as simple as possible. And we tried to attribute sources for every slide that we have in here, but it started to get a little bit busy, so we decided to just basically attribute many of the charts and graphs you'll see in here come from ASHRAE, or the American Society of Heating, Refrigeration, and Air Conditioning Engineers.
And one final point, there's also been a slight adjustment to the slides, so your handouts may be different, but the content is the same.
Right, and we'll show you when we get to that. So some of the initial issues with this is, why should we care about energy and energy auditing? Because it increases energy awareness and concern, and today more than ever, we know how important it is with some of the things that have gone on recently with crises in the Middle East and natural disasters in Japan with nuclear power accidents as a result, which is causing very unstable energy costs. We have oil at $100 to $110 a barrel. Electricity costs are going up every year, and an increasing global demand. We'll get into some of that later on, where some of the developing world's thirst for energy is growing exponentially. And energy costs really wreak havoc with budgets. Some of our clients have seen 50 and 60 and 70% increases in the course of 1 year in their energy budgets, and that really makes it difficult, especially today. As we all know, most governments and a lot of businesses are in very tough shape right now. And it's also very important as an asset preservation investment, because you can fix a lot of things about buildings that it increases the lifetime of the building while saving you money throughout the lifetime of that building. And we really view energy efficiency as the gateway to sustainability. A lot of companies and institutions today who are trying to be more green and more sustainable, and a lot of those attributes that they're looking for don't have tangible economic benefits to them, but energy efficiency does, and it really is a great way to get started. We're going to go through a couple of slides very quickly just to sort of put a point on why we should care, especially here in the U.S. This chart, even though it's a few years old, it's still perfectly applicable to what's going on today, where we use at least 3 to 4 times the energy per capita than virtually all the other westernized countries in the world. And even the growing countries like China and India, we use much more energy per person. And buildings themselves, which all of you are involved in through AIA and through the architectural field, where buildings are the single most important contributor to greenhouse gas emissions that cause climate change based on studies done by the Pew Center on global climate change. And just the annual energy waste in the U.S. alone is equal to $300 billion, which is a huge amount of money. And just the power plant waste heat from our power plants are equal to the total Japanese energy use. And our economy in general uses twice the energy per capita as they do in the European Union. So it shows you that it's a very important issue here in the U.S. And I'm not going to read this to you, but this is a quote from Henry Ford that shows if you really care as a professional about this, you really can make a difference. So if you think you can get things done, it's all a matter of willpower and working with your teammates and your clients to get things done. And as many of you have seen, especially those of you that are become LEED accredited professionals in the past few years, greening and cleaning up is becoming a larger and larger part of every business, no matter what it is, whether it's from hospitals and schools to major corporations around the world. It's becoming bigger and bigger. And I'm not going to go through all these, but a lot of these companies are taking this very, very seriously today. And as we all know, oil prices continue to rise. I picked out this slide from an older presentation I had done and realized it's actually pretty applicable to today, where you can see the highest it had been basically in our recent history was just after Hurricanes Katrina and Rita at $70 a barrel. That didn't count a few years afterwards where speculation in the market had caused oil to go up to $140 a barrel. And then as the economy plunged in 2008, it went down to $30 to $35 a barrel, the historic lows or historic averages in some cases. And now here we are back up again to $100 to $110 a barrel today. And one of the main causes of that is the rising increased energy use by China and India primarily, most of the developing world, but primarily China and India. And again, I'm not going to go through the details of the numbers on this slide, but all of you know, just anecdotally, that China and India are continuing to use more and more energy, and that much energy that gets used there is some resource that we cannot get in this country. And it's putting a large strain on energy reserves around the world. And finally, another reason why we should care is climate change. And there's an increased global awareness of the need to reduce our carbon emissions, which we know is an extremely important issue for many, many people. And our building stock, just in the U.S. alone, uses over 50% of the total electric use for the country, which is something we all in this industry can have a great impact on. And the U.S. Environmental Protection Agency, or EPA, has recognized that deep energy retrofits of existing buildings is the fastest and most cost-effective way to reduce our carbon emissions. So we can make all the new LEED Platinum buildings we like, but doing deep retrofits into the huge building stock that we have, millions and millions of existing buildings, is really the keys to the castle in trying to affect climate change in this country. So I'm going to quickly go through some energy fundamentals. Some of you have learned in the past. For those of you who hadn't, the British thermal unit, which is what we use in this country, and it turns out we're basically the only country left in the world, not even the Brits use the British thermal unit anymore, is the heat required to raise the temperature of 1 pound of water by 1 degree Fahrenheit, or about 1 match, which is sort of a very classical interpretation of it. But it goes throughout the rest of our presentation, where virtually all energy in the U.S. is measured in BTUs. Even electricity gets converted over to BTUs from kilowatt hours. Some other common units of measurement or electricity are either in kilowatt, which is an instantaneous usage of electricity. It measures almost like a miles per gallon of a car. And a kilowatt hour is the electricity used actually consumed over a period of time in 1 hour increments. There's fuel oil, which virtually everyone is familiar with. This is measured in gallons. It's 140,000 BTUs per gallon. Natural gas is measured in cubic feet. And there's about 100,000 BTUs per therm in natural gas. And liquid propane isn't used as often, but that's about 92,000 BTUs per gallon. And again, I'm not going to go through all of these, but it's great takeaway information for you as you get more and more involved in energy within your own practices. These are some nice conversion factors to be able to use. Now, this is something that's very important as we get further on into the presentation where Paul takes over and gets into the real technical details. But the R value and U value are basically an inverse relationship. R value is the resistance of a material has to heat flow, so most wall enclosures get measured in R value. U value is a measure of the material's conductivity of heat. So a lot of windows, in many cases, are spec'd based on their U value. And they relate by the U value being 1 over the R value. So it's a pretty easy connection to make between the two of them. This is a little slide we picked up where we're describing many different building types and showing the energy use both above the median and below the median for these building types. And some of them are pretty straightforward. You would expect, an apartment building where most people are gone during the day to be relatively low in energy use per square foot per year. And a church, of course, it only really gets used once a week primarily. But things like offices don't have as much use on a per square foot basis per year as others, because if you think about it, after about 6 or 7 o'clock at night, most office buildings are closed. And they're closed all weekend for the most part. But other things like supermarkets and swimming pools and community centers and colleges where you have dormitories that are running 24/7 in many cases have an awful lot of energy use. And sometimes have a median use of above 200 and 300 BTUs per square foot.
And this is important from a benchmarking standpoint. This is one of the places we try to begin our auditing process for our clients, is to secure their energy bills in advance so that we can develop an energy use profile of them for a year and see what their energy use per square foot is, because this will help us understand how they compare to their peer buildings in a given climate zone. And this, another very valuable tool for this is the Energy Star Building Portfolio Manager that is offered by the Environmental Protection Agency. So this benchmarking tells you where you're starting from in terms of the general efficiency of the building.
And for those of you who want to look up more information about that, you go to www.energystar.gov. And it's a fabulous website. They've really put a lot of money and effort into it over the past few years. Next, we want to talk about the building impact. U.S. energy and carbon emissions, where we've compared the energy use in industry, transportation, and buildings. And you can see, as we mentioned earlier, buildings make up roughly half of all the energy use in the country. Electric use makes up much, much more of it. As you can tell, that the influence of vehicles really skews that, because gasoline then becomes the major fossil fuel provider in the transport sector. But buildings have the largest influence by far in electric use in the country. And then CO2 production, again, industry is down in the 20s, transport is about a third of the value, and buildings, again, are almost half of the carbon emissions in the country. So if you can have an impact in buildings, you can have a great impact on overall carbon reduction. Now, energy, as some of you may know, is a very large expense in most buildings. This is information that comes from the BOMA exchange report. It's about 7 or 8 years old, and they've updated it once or twice. But the energy costs back then were 20%, and they continue to increase and become a larger and larger share of that pie over time. And it's something that if you can spend a lot of time or a fair amount of time thinking about how to reduce those utility costs in buildings, for an owner-occupied building, it can help deliver profit back to the bottom line. In the electricity consumption, you can see where cooling is the largest single component of electricity. Lighting is another quarter of it, and office equipment uses about a quarter of all the electricity in buildings. And that number is going to continue to increase over time. Even though we get more efficient equipment, we're getting more and more of it. Everyone could look around their office now and see where 15 years ago you maybe had a coffee pot or something, and now you've got laser printers, multiple computers, fax machines, plasma screens, all kinds of things. It's really contributing a lot to electricity use in buildings. All right, now I'm going to turn it over to Paul to talk some more about the enclosure elements of buildings.
Okay, thank you, Chris. What I've done here is just identified the key components that make up the foundation, from the foundation to the roof of our building. So what we've defined the enclosure as is those elements that constitute the envelope that surrounds the occupied space. And of course, if this is significant in defining that edge, because nature likes uniformity and consistency, and if we want our occupied space to vary from the outdoor temperature and humidity conditions that change on an hourly, a daily, and a seasonally basis, we have to invest energy to make that happen. And so we will be focused on foundations, the walls, windows, doors, roofs, and the various components that make up that shell of our buildings. And in terms of the energy interaction of the building with the environment, there are the three standard methods of heat exchange. Conduction, this is where there's a direct transfer of energy from a warmer to a colder material through straight conduction. Imagine putting your hand on a slab of marble or touching a glass window. It feels cold to the touch because it's such an effective conductor and draws heat from the hand. Convection is that mechanism that's driven by a change in temperature of air between a warmer and a cooler surface, so that warming air on a sunny south window will rise and induce cooler air off the floor behind it. And likewise in the winter, that same window, through a cooling effect, will cause air to be cooled and sink to the floor. And this is why many of our mechanical heating systems provide for heating under the windows of our buildings. The radiation component is an indirect heat transfer from a hotter body to a colder body, and it is the temperature difference to the fourth power. And radiation is not a method of heat transfer that we often recognize or account for. And if you can imagine sitting across from your fireplace on a cold winter's night, you're feeling the warmth of that radiation because the temperature is over 1,000 degrees on the fire. Your skin temperature may be 80 or 90 degrees, and it is transferring that heat from the hotter to the colder surface as a function of the fourth power of that difference. The same thing happens with glass in our buildings, because glass is an excellent transmitter of infrared radiation, and so we will be on a cold winter day in our building. If we're sitting in front of a glass window, we will be trying to heat the great outdoors and with our body warmth, and that effect can lead to chills that we don't always recognize. And then the other mechanism has to do with humidity and moisture, because again, moisture contains a significant amount of energy, and the transfer of that between an occupied and unoccupied, indoors and outdoors, involves a transfer of significant energy. And here again at our enclosure boundary, this graphic shows the various mechanisms involved. There is energy transfer via air pressure differences, by solar effects, by thermal effects with the outdoors. Wind can have a very major effect on moisture transfer. And then vapor pressure. If we're in an air-conditioned building in the summer and it's very hot and humid outside, we dehumidify the interior space, and there's a high humidity content outside. That vapor pressure differential will cause moisture transfer through our enclosure boundary, and we need to manage that carefully and effectively in our building design. So here's some examples of what I described a little earlier. Conduction would be the straight transfer of energy from the inside, where I've seen buildings with precast concrete members. Their segments of them extend to the inside, to the heated and cooled areas, and the outside are in direct contact with the environment, and they are a real source of conduction and energy transfer. The same thing with the slab. The foundation is in contact with the earth, and the earth is fairly stable in temperature, but nonetheless often at a different temperature than the occupied space. In terms of conduction and radiation, again, radiation most often will come or will feel the direct effect through windows, but in the summertime, a hot summer day with sun beating on the roof and that roof assembly heating up, it will radiate energy into the occupied space and have a direct effect on increasing the cooling load. Similarly, within our spaces, there are internal gains that contribute to overall heat transfer from lights and appliances to the occupants. In terms of the audit process, we wanted to just run through quickly the steps involved in the audit. And what we see here is our screen is showing some condensed graphics. I'm not sure if you're seeing that as well. But that first bullet point deals with gathering energy use data. And here again, that I referred to earlier, where energy use data for a year and square footage of the building will give us, by totaling the electric and fossil fuel use, will tell us what the energy use is for that building and how it compares to its peers. Another important part of our audit is to interview the knowledgeable people within the building to understand issues that they may have. Building maintenance folks and occupants can give us insight into how the building is operating and if there's particular problem areas they may experience. We would want to perform a walkthrough of the various utility spaces and the basement. We'd want to inspect the spaces above the ceilings to look for various impacts where the enclosure may be experiencing some effect from the environment, or to see the construction details that would give us some insight into the efficiency of the enclosure. And finally, we'd want to walk the building exterior carefully, inspect the roof, look at wall to window interfaces, and make sure that any telltale signs of moisture migration or air movement, they will become noticeable and allow us to, or help us understand how this building is operating and performing, and places to look for further difficulties or opportunities. It's very important to understand also the motivation for performing an audit. If a client is interested in a quick way to reduce energy costs, then it's important to understand that, because it will rule out the possibility of major capital investments that you might look at by if the owner is committed to a sustainability program, or is looking to implement a capital renewal program where they would upgrade the building enclosure and various mechanical and electrical systems to renew the building. And also, it could be a effort to do a building energy performance assessment as a prelude for sale, where, again, there is a protocol established under ASTM Standard 2797 that describes a way to evaluate a building as for information to be provided to a purchaser. When we talk about enclosure elements, one of the most important ones architecturally are windows. Windows have a big effect on a building and its energy efficiency. There are a number of forces and energy transfer mechanisms involved in the building, in glazing systems. We mentioned direct solar radiation. Glazing is very good at transmitting approximately 75% of the solar spectrum, and as much as 85% of the visual spectrum, which is why it's such a nice component for architectural purposes, to provide for a visual connection to the environment. But similarly, it is a very good conductor, and so it is a source of significant heat gain and heat loss, and radiant effect, either inward or outward, on the occupants. When we think of the enclosure, it's important to recognize that glazing is part of an overall wall assembly, and so that you can, if you want a high-performance building, then you need to look at it as a system holistically, including not only the wall elements, the opaque wall elements, but also the quantity and quality of the glazing systems. And so many glass buildings, nearly all glass buildings, are visually stunning, but from an energy standpoint are quite inefficient. And there is more and more attention being paid to the wall-to-window ratio, as the awareness created by the U.S. Green Building Council and others of building efficiency and effectiveness has begun to influence the design community. Another important heat transfer mechanism is infiltration in buildings. And there are a number of mechanisms that contribute to infiltration. You can have a condition of air leakage caused by wind effects and wind pressure, and there can be a stack effect that results in warm air rising and creating a chimney effect internally to a building, and creating a pressure gradient from bottom to top, and then also the effect of the mechanical systems. What is the energy balance in the building?
This is Chris. Some of you may have felt that stack effect when you go into some urban areas and downtowns where they have links between buildings above ground. I've seen a lot of this here in Hartford, in Calgary, in Minneapolis, and other cities, where the stack effect of the taller buildings that are connected to lower buildings, you may walk out into that link and there's a huge rush of air from that link as you enter it. We used to run into that here in the Travelers Tower in downtown Hartford, where it really felt like a 10 or 15 mile an hour wind in your face as you went from the one building to the next. And that was a very significant stack effect due to an older tower with elevator machine rooms at the top where the wind would just whistle through and draw the air from every opening it could.
So this next slide describes, again, more of this energy transfer caused by air movement. And this slide shows that the mechanical system can also have a significant effect on this, because when we set up our ventilation systems, we often try to do a balancing at the startup of the building, a balance between outdoor air for good air quality and then exhaust air from the building to maintain just a slight pressurization so that air can be conditioned, humidity can be controlled, and you won't get intrusion of unconditioned air from outside. If over time that fan balance is upset, it can create real difficulties and fundamentally change that those relationships. And this is very important in places like hospitals or certain research areas where control of air movement within a building and within certain spaces is critical. And so this shows, this next graphic speaks to the stack effect that Chris had described. That left graphic shows a neutral pressure level where the flow of air is typically inward at the bottom and outward at the top, again caused by the thermal buoyancy of air. The middle graphic shows the effect that you may experience from wind pressure on the side of a building, where it will drive outdoor air into the building through crackage and actually draw it out on the leeward side. And when you combine those two forces, you can see the net effect where you tend to have air entering a building at the bottom and exhausting from a building at the top. And again, this applies to tall buildings. This effect is much less dramatic in a 2 to 5 story building, whereas if you get to a 20-story and higher building, it can become very significant. As auditors, what we do is, again, try to understand the significance of this air balance effect on buildings. And so we are always prone to checking draft at the entrance doors, because this gives us just a quick sense of whether a building is positively or negatively pressurized. There are non-toxic smoke pencils that can be used to also show this visually, and just something as simple as pulling on a door and seeing what kind of resistance there is will also give you an insight into the air movement and relative pressure condition between the interior and exterior of a building. Fog machines are helpful in this way as well. Theatrical fog machines can create a large cloud of non-toxic smoke that can give you a very excellent visual impact and image of where air is leaking into or out of a building. We can do a paper study and look at the balance between exhaust and makeup air quantities for a building. If there's current data, this always has to be taken with a grain of salt if you're looking at original design drawings, because things will invariably change over time with a building. And likewise, you can look for various telltale evidence in the visual observation of the building in the interior and exterior. You might be able to see evidence of staining or other characteristics where air leakage is marking the side of a building. And on the inside, you might be able to feel drafts or observe daylight if you look above the ceiling. A lot of this infiltration can again be quantified with a new, more affordable development in terms of infiltration testing using blower doors. This is something that's perhaps more common in the residential area, but can be done very effectively in larger commercial buildings. It may require that instead of doing a full building infiltration test, that a floor-by-floor or even a segmented portion of a floor be tested and quantified to help quantify the amount of air movement and exchange within a space.
And this is Chris again. I recently had this done in my own house and was amazed at the results where they were pulling, I think, 3,000 CFM through that door. And you can see that the graphic there shows sort of a fake door that they put in place with a large fan, and it draws air out through your house. So it brings air through windows, through cracks in the foundation and the sill and so on. And after sealing cracks and things that they found around my house, they were able to reduce that infiltration by more than 10 to 15%, which there was a noticeable difference in our house. It was slightly warmer once that was completed. So it saved energy and also made it more comfortable. So I think it's a great opportunity for homes as well as small to medium-sized commercial buildings.
Likewise, this technology can be very effectively combined with infrared technology, because if you perform an infiltration test in a building, again, it doesn't have to be the whole building that's done at once. You might do, again, as I mentioned, a floor-by-floor approach. If you do this on a day when there's a significant temperature difference, at least 10 degrees between inside and outside, and you use an infrared camera, sources of air leakage will be illuminated and can quickly pinpoint the physical location of this, and it can be done. Guided air sealing can be performed very effectively using these two technologies to document, locate, and correct infiltration in the building. Infiltration can be responsible for up to 50% of the building energy use in smaller buildings if the construction was not well executed and attention was not paid to the details of sealing at components interfaces. Other things that affect building occupants include things like air temperature and movement. We've alluded to this, and again, with the client interview, some of these things can come to the forefront that will help guide us as we do our audit. We will look for the effects of air temperature and air movement because they have a big effect. A draft effect on the occupants can cause them to be very uncomfortable. It can also, the relative humidity within a space can be a big factor. If you're effectively controlling relative humidity in the summertime, occupants can tolerate a much higher dry bulb temperature within the space. And interest in controlling relative humidity is very important from a building preservation aspect as well, because unmanaged intrusion of moisture into or out of a building can cause significant damage that would have costly impacts on repair. The activity level that is occurring is also a big factor for occupant comfort. So if it's an industrial site and there's physical work going on, those employees and occupants will be having an additional heat source that will not be present if you're in an office building with sedentary work environment. And again, thermal radiation effects. Are there hot or cold surfaces directly in a line of sight relationship to occupants? Because infrared radiation is like light from a lamp. You need to be in a line of sight relationship. It doesn't go around corners, doesn't have that effect. And then also the clothing. Sometimes this, again, you need to be aware of these things. They affect occupants, and they will also may be related to complaints that are received because people are or are not dressing appropriately. And then there's other things too, such as the intangibles like relationships with the manager, or other things that can really affect the way we feel.
Right. Which may not be directly related to work, as you can tell by our funny graphic there.
Yeah. Or fixable by audits.
Right.
This is a graph showing from ASHRAE Standard 55, which deals with human comfort. And what this shows is the effect of clothing, for instance, and humidity on the what is deemed to be an acceptable range of comfort conditions for building occupants. And so you can see that with higher moisture levels, that cooler temperatures become more acceptable. So in the wintertime, if there is a method of humidifying a space, it would allow that space to feel more comfortable, even though the humidity is higher at a lower temperature. Conversely, in the summertime, high humidity makes the dry bulb air temperature less tolerable to occupants. And by taking the edge off with some form of dehumidification in the summertime, warmer temperatures are very nicely tolerated by building occupants. Now this next graph and slide discuss these temperature conditions and again what standard kinds of settings are, and they make reference to a dissatisfaction range. And from testing, it's been determined that these temperatures and these temperature ranges will be tolerated by up to 90% of the people for each of those given settings. And it's important in performing an audit to understand what these, if there are any internal processes or procedures or standards established that set the temperature set points for the occupied space, because again this will give you a better understanding so that you can do a more informed audit and understand how effects of the enclosure can play into a comfort perception of use the building occupants.
That's one of the things that we find as auditors as a notoriously difficult thing to nail down, is what those set points really are and how they're changed. Because as all of you that may have worked in big offices, either now or in the past, if occupants have access to those thermostats, there's all kinds of games being played and turf wars going on between who has control of the thermostat and who doesn't. And I've seen everything from lock boxes being put over thermostats, with people trying to defeat them by putting a bag of frozen peas over or putting their lighter under it and all kinds of different things to affect that thermostat. And a lot of it has to do, honestly, with the lack of proper building enclosure technology and maintenance. You know, from the way the building was designed and built at the beginning to the way it's been maintained over time. And so it directly affects what you guys are involved in every single day.
And going back to the issue of moisture management, high humidity can result in discomfort with occupants and in their ability to reject heat. And it can also cause microbiological problems where any moisture that condenses out will potentially support the development of mold. The formula for mold is moderate temperatures plus water plus a nutrient. And so when you look at something like sheetrock, the paper covering on sheetrock is the nutrient that mold likes, and if you get a condition where you have a high humidity condition inside and there's a direct thermal bridge to the back side of the sheetrock, you can get condensation on the sheetrock that will potentially result in growth of mold, because mold is ever present in the air.
And up until recently, in most of the northern half of the country, air conditioning was never installed in most schools, as an example, right? For those of you like me who went to school many years ago, we didn't have air conditioning. But now most schools, regardless of where they're located, are getting air conditioning in their original designs, and it's mainly due to mold. And even with a lot of the buildings that we work in all the time, even when school systems aren't using the buildings for the summer, they keep them temperately cool, not down to the set point they would when people are there, when students and staff are there, but they keep it to at least a moderate temperature in the low 80s, say, and keep the air conditioning running throughout the summer to prevent mold buildup. So again, that could be something where your building enclosure or lack of a proper building enclosure could help make it easier for mold to grow, and the school system has got to spend a lot more money on energy use in the summer, which typically, depending on where you are in the country, the energy costs in the summer can be double what they are in the winter. So that's another very important sort of takeaway point from this, is that the building enclosure really has a very, very big effect on what goes on in costs, and sometimes in indirect ways like mold prevention.
And Chris points to a good issue here, because older buildings that were not designed for air conditioning, that have been air conditioned, can often develop problems because of that change in their basic method of operation. There are many older buildings that have lath and plaster, perhaps a brick exterior with an air space and then a lath and plaster interior. And if you add air conditioning to that building, what you will find is there is the potential, because there is an absence of a vapor barrier, there's a possibility that moisture will come through the wall and can actually cause the degradation of the plaster so that it self-destructs over time. And this is, again, a function of the vapor pressure difference between a warm, moist exterior and an air-conditioned, dehumidified space on the interior. And, again, that can have effects both on the occupants from a health perspective. Many building owners fear the use of the term mold, and they know the effect it can have on indoor air quality, and the cost of the abatement is quite significant. And again, humidity control in the wintertime, it causes low humidity conditions cause dryness in our mucous membranes. It can increase the health difficulties and transfer of colds and viruses. And it can also cause shrinkage in hygroscopic materials such as wood and the like, where quick changes in humidity level can actually cause wood to split and crack. And then there's also issues related to static electricity buildup that can play havoc with IT systems. This is an example of the WUFI software that was developed by Oak Ridge National Lab. That is a tool for determining the dynamic one-dimensional effect of moisture and heat transfer through a multi-component building envelope. And this is a very useful tool and can help keep designers and builders out of trouble by highlighting any places where the permeability of that combined assembly may lead to moisture intrusion or export that could have an adverse effect on the building enclosure. And here's a psychometric chart. The point that this makes, the bottom of that graph shows, or of the chart, is dry bulb temperature, and the vertical right line is the moisture content of an air and water vapor mixture. And so the bottom shows that as you move to the left and with colder temperatures, the amount of moisture that can be held in an air water vapor mixture decreases. And this is again a problem when you have, for instance, penetrations through your building enclosure, such as unit ventilators in a school system, or various ductwork penetrations or utilities, and any air leakage around those penetrations in the wintertime can result in warm, moist air on the inside coming through those breaches in the enclosure and finding a cold surface that results in condensation. And that mechanism can lead to accelerated deterioration of enclosure components and systems. And so this is where, again, air leakage needs to be controlled, and enclosure assemblies need to be carefully engineered to manage any moisture vapor pressure difference between interior and exterior conditions. Another significant element is issues related to wind effects. And again, in our interview process, we try to understand if there's any issues related to indoor air quality or odor entrainment and things of that nature. And what this diagram shows is that if we were on the plains of the Midwest where it's flat and open, you will get a fully developed wind regime within a few feet of the ground, where you'll have high velocity or full velocity of wind. And but when you have obstructions like a forest or a building, that wind impacting with that obstruction will cause recirculation and eddy currents and things of that nature that can have a big effect on entrainment of odors and other contaminants on the exterior of a building. And where this becomes significant is related to things like the location of a boiler stack or an intake air louver for an air handling system where, again, prevailing winds, or even if it happens intermittently, it may be that prevailing winds don't ordinarily cause this problem, but a certain wind orientation striking a building could lead to entrainment and some of these problems that you may have heard about in the interview with building occupants.
And this is Chris again. I've seen this on several occasions where we're on a roof of a building somewhere, and the outside air intake will be no more than 10 feet, say, from an exhaust. And sometimes it's a toilet exhaust, sometimes it's a kitchen exhaust, and it causes, terrible complaints and problems from the building occupants because they're smelling these things that should be taken away in the airflow, but it just doesn't happen because of the way it was designed. Or sometimes chimney stacks that are just not quite tall enough. And when you sometimes get thermal temperature inversions, it really can cause significant problems with buildings where the stack was designed with the anticipation of having warm air rising, helping to sort of float the contaminants away. And if it's being capped, like we have in some cities here in the U.S., those contaminants can stay low to the ground and then be sucked into the building. So it's something to think about when you're designing building enclosures, where those penetrations are going to be, and make sure that there's a certain safety factor being built into the design to try to take into account any sort of weather occurrence that might occur there.
Now, this next slide goes back to re-examining the glazing components of a building enclosure. And again, we're approaching this from the perspective of the auditors who've been commissioned by a building owner or manager to come in and evaluate the building. And many of our building systems have a design useful life. We don't expect our cars to last forever, and so we will often renew them. Well, building systems are very similar. A roof won't last forever, and it may have a membrane roof, or a built-up roof may have a useful life of 10 to 40 years, and at some point will need to be renewed. And our building stock has similar needs, and capital renewal is often the motivator for us to get involved in auditing existing buildings. And so when we, again, look at the potential energy impact of glazing in the building enclosure and its effect on heat loss in the winter by radiation to the outdoors through glazing assemblies, or heat gain in the summer from solar orientation that adds to our cooling load, or the conductive effects of glass and their contribution to drafts and convective heat gains and heat losses. These are big opportunities to look at if glazing replacement is under consideration. And these are a list of some of the options that we'll discuss regarding glazing replacement. One of them is to upgrade the glazing assembly itself to go to a higher quality glass, perhaps one with selective coatings on it. Another method is to optimize the glazing by orientation, to use a high transmission glazing where there are areas such as in a classroom or a place that can take advantage of natural daylighting and to put selective coatings on glass by orientation so that the afternoon, late day solar gain in the western glass is minimized in terms of its effect on glare and cooling load creation. Also, the positioning of the glazing within the opening. If you're going to reglaze windows, there may be opportunities to reset where the glass sits within the enclosure opening, and also the percentage of glass, the glass-to-wall ratio that we discussed earlier, as well as physical additions that can be made to the building to manage solar gain in windows. So here's an example of some of the advancements in technology where this graph shows the effective range available using a double glazed window assembly with various types of filler for gas between the glazings, and also with various coatings on the surfaces of the two sheets of glass. So the top of that graph shows a air, argon, and krypton-filled glass assembly starting from the top with an emissivity of 0.84. Now, the perfect emitter and the perfect absorber is a black body, and so a black body would have an emission value of 1. And so the lower the E value, the more reflective it is to infrared radiation. And so the bottom three lines show a selectively coated double glazed assembly where you have the selective surface applied to the glazing surface 2 or 3. That's the space between the two glasses, and it's a low E coating of 0.1, and what that will do is hold in energy. It would be a very good selection for a northern climate where you would reduce the radiative heat loss through that window assembly in the winter. This next slide shows a similar effect on the overall U factor of a window assembly using triple glaze windows. And again, there's been great advances in this technology. The cost is becoming more cost effective, and if you have an owner who insists on lots of glass, this is a consideration. There are some absolute limits to what can be done, though, in terms of refitting existing window frames with a triple glaze window assembly, because this will tend to be a larger assembly, and so you need greater depth in that window frame to support that, and also there's greater weight involved, and so the size of a triple glaze assembly has some natural limits as well. And here again you can see the effect of coatings, and this is where, again, by selectively putting appropriate coatings by orientation, you can optimize the benefit of new glazing replacement. This shows retrofit options relative to the location of the glazing within a wall assembly. And the top left side shows the effect of glazing that is located in a deep recess on the exterior of the building. This contributes to significant cooling or heating of that glass and will promote significantly higher natural convection in the building. And when compared to the right-hand side that shows the glazing closer to the interior space, that would allow less environmental effect by the glass. The bottom two slides show the effect of adding curtains or window treatment inside the building. This can be a much lower cost method of improving the efficiency of window systems, and by having it on the having the glass on the outside and locating the shade on the inside of the penetration, you can create problems with moisture and condensation in the winter with that kind of an assembly, whereas having some adequate spacing between the glazing and the shading would allow for sufficient natural convection, as shown in the lower right-hand corner, to avoid significant moisture buildup in the winter with a higher humidity condition inside. This shows the effect of modification to the window-to-wall ratio on annual energy use. And they show here two sites, Chicago and Houston, and the left side shows without natural daylighting and with daylighting. And what's important to notice, these graphs are based on the kilowatt-hour use per square foot of floor per year, and what it's showing is that in Chicago, the lower in all cases, the lower of window-to-wall ratio, the more efficient the enclosure is, and as that percentage of glass increases, so increases the energy use requirements. And you can see that positive utilization of daylighting has a significant effect in reducing the energy requirements of building operation. Similarly, in Houston, you can see a big effect related to the requirements for mechanical cooling in a space when you have high glass-to-wall ratios. Oh, sorry, I'm a little too fast there. This next slide shows the impact of another way that solar effects through glazing can be affected is by the addition of various fins or other building assemblies on the outside of windows to provide for natural shading. What this slide shows is an overhang that is engineered to provide for solar gain with low sun angles in the winter when internal gain from the sun would be useful, and yet that solar arc in the summertime would move the sun higher overhead, providing effective shading and reduction in direct solar gain through this window assembly. And this particular slide may be different than the one that you have in your handout because this was shuffled with another slide. But it expresses the same concept, the idea of using building elements, either the addition of or the optimization of building elements to help manage solar control effectively. Next chart shows insulation options, because when we talk about an audit, if it's leading to an envelope, an enclosure thermal improvement, we have a wide variety of materials available to us, including traditional fiberglass bats and rock wool, and these can come in bats or in rigid boards. And this table shows the various foams, such as polyisocyanurate and spray urethane foam, which is come into greater use and is very effective in sealing leakage and providing a more complete insulation of an enclosure wall assembly, and it can also provide an effective thermal barrier and break where there may be currently elements within the wall enclosure that provide a direct conduction path to the outside. There's always a question that comes up regarding what's the right thickness of insulation, and many of our codes require certain minimum amounts of insulation in wall and roof assemblies, and if there's going to be a gut rehab of a building or a major renovation, it may trigger, the dollar value of that upgrade may trigger the requirement that you bring a building into code compliance. This graph shows two basic elements that affect the cost effectiveness of insulation. The lower graph starting on the left shows the relative economic cost of adding multiple layers of insulation. The next line shows the overall cost of energy for a building, and it shows annually that first inch of insulation will really help to lower the energy cost, and then as the thickness increases to the right, it will further reduce the loss. Where those two lines cross create they point to an area of optimum insulation thickness as a function of annual operating cost. And it's important, if any major rehabilitation and renewal of a building is taking place, that we not be driven solely by this first cost, because again, the operating cost of a building over its life will dwarf the first cost of some of these insulation and new glazing assemblies. In our audit, advances in infrared thermal imaging technology has really made this a much more accessible and affordable tool for auditing. And this example here shows the design of a stair tower in a high-rise building, and the steel framing that surrounded that had multiple points of direct thermal conduction that light up very well here, and you can, this points it out. And again, in a re-insulation of this wall enclosure, careful consideration should be given to applying insulation to provide a thermal break to reduce this energy loss. All things being equal, you would ideally apply insulation on the exterior of a building if you were going to add more insulation, because in that way you capture the thermal mass of the enclosure within the insulated boundary, and this helps to make interior temperatures more uniform with a lower day to night and summer to winter temperature variation. That's not always possible for aesthetic reasons and other reasons, including moisture transmission and vapor control, so this needs to be carefully assessed. This graph shows the effect of fabrics such that can be used for drapes, and again, the various materials should be carefully evaluated so that you may choose window treatment on the north side that allows good energy transmittance and daylighting, whereas on the south side it would be more opaque for solar control purposes. And then another important element that we look for in inspecting our building enclosures is the use of caulking around enclosure assemblies, transitions from wall to window assemblies, from wall to foundations, and so on. There's sometimes a liberal use of caulking for materials with the hopes that it will seal all ills of poor installation, but recognizing the differential expansion between materials such as metal and concrete, or metal and brick, or the installation and the proper selection of sealants is vital, because with flexing over time, they will fail and potentially be a source of energy loss and water intrusion.
All right, this is Chris again. I'm going to take over here for the last few slides before we finish up. Once we've looked at all of the baseline conditions, we've looked at all the options to retrofit the building and make other low-cost, no-cost improvements through, repairing sealants and so on in the building. We then have to put together budget pricing for the clients to come up with an idea of how much is it going to cost the client to install all these measures, both design, install, in many cases commission these measures as well. And we have to calculate the energy savings. A lot of that is done through building energy simulation modeling, which I know in May this same group is going to be holding a seminar on that with my friend Eric Oliver is going to be teaching that course. So typically we then come up with what we call an ECM, or Energy Conservation Measure Summary Table, which usually goes in the executive summary of our building audit, which does a good job of summarizing for the client in one place basically the list of the measures, the total project cost of each measure, any utility incentives or state incentives that might be available. If it's, in this case, this was taken from the Energy Savings Performance Contract, that the total finance cost is, and what the expected savings are on an annual basis. And then usually either a simple payback methodology of calculating return, or we tend to prefer a life cycle cost analysis, which takes the ever-increasing cost of energy into account, as well as maintenance costs into account. And the labor for maintenance costs and material costs continue to increase year after year after year. And we selected this one that had an example of to building enclosure upgrades that had been recommended and were in fact installed. This is a project we were involved in from 2005 to about 2008. And I don't know if you can read it clearly, but that's roughly $1 million window upgrade as part of a $5.5 million project. So 20% of this whole project was replacing windows in this 1965 vintage high school. Same thing with insulating one of the buildings. It was another $95,000, almost $100,000 worth of insulation. And you can see both of these were relatively high payback measures. The windows were a 30-year payback measure. The insulation was a 13-year payback measure. But these really had huge impacts on the school children. In this high school, some of these kids would come to class in a parka and could see their breath on the coldest of days. So this, from a mission point of view of teaching the kids in a comfortable thermal environment, had a huge impact on these schools.
And as Chris mentioned, it's bundling the low-cost, no-cost measures such as lighting replacement and tuning of the HVAC controls that help to carry this, make this a viable financial project.
Right, and so that's one thing we always recommend when you're looking at an energy audit. Always try to convince the owner, the manager, whoever it is, to not just pick off the low-hanging fruit, but to take a look at the whole opportunity, the set of opportunities in a bundled way, a more holistic way, so you can use these low-cost measures to really get deep impacts. You know, like this deep retrofit we talked about in the very first few slides that EPA recommends. It really has a big, big difference. And the life cycle cost analysis, really, as I mentioned a minute or two ago, is the best way to really truly value over the long term what these costs and savings are. So with that pretty much finishes up the presentation we have for today. We've got our contact information here. If you have any other questions on this topic or others relating to energy or sustainability, please feel free to shoot us an email or give us a call. With that, we'll turn it back over to David for a quick wrap-up.
And that does wrap up today's presentation, Energy Auditing in Relation to Building Enclosures, sponsored by the American Institute of Architects and presented by Chris Halpin and Paul Poppenshaw. And by the way, at the end of the program, we will be asking you to complete an online program evaluation. Please take a moment to fill it out. Your feedback will help us to continue to bring you future quality programming. Today's program is copyright 2011, the American Institute of Architects. All rights reserved. Thank you for joining us today, and enjoy the rest of your day. You may disconnect now.